This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
At Collide, we know end users are IT admins' most significant untapped resources and key to solving the most challenging to fix security issues, including instructing developers to set passphrases on unencrypted SSH keys, finding plain text two-factor backup codes and teaching end users how to store them securely, convincing employees to uninstall evil browser extensions that may sell their browser history. Visit collide.com/SERadio to sign up today. That's KOLIDE.com/SERadio. Enter your email when prompted to receive your free Collide gift bundle after trial activation. You can try Collide with all its features on an unlimited number of devices for free for 14 days. No credit card required. Try it out at collide.com/SERadio.
This is Philip Winston with Software Engineering Radio. Today, my guest is Dr. Richard Seitz. Dr. Seitz has spent most of his career at the boundary between hardware and software, with a particular interest in CPU software performance interactions. His past work includes VAX microcode, DEC Alpha co-architect, and inventing the hardware performance counters you see in many CPUs today. He has done low overhead microcode and software tracing at DEC, Adobe, Google, and Tesla. Dr. Seitz earned his PhD at Stanford in 1974. He holds 66 patents and is a member of the U.S. National Academy of Engineering. Let's start at the top. What are software dynamics, and what benefits are there in striving to understand them?
Well, software dynamics refers to different programs or different threads of a single program or the operating system all interacting with each other. The contrast would be with static software, a program that you start and it runs and it finishes. And each time you do run it, it does sort of the same thing at about the same speed, like benchmarks. But real software, more and more today, is time-sensitive and has lots of user-facing work to be done or responses to give. And that dynamically ends up interacting with all the other things running on a computer, not just standalone like a benchmark. So if you look at something like Activity Monitor or Top or Task Manager, depending on your operating system, you'll find there's like 300 different programs running. So software dynamics refers to the interactions between all of these in trying to get responses back to something that's time sensitive, a person or a robot or something in motion that needs responses quite quickly.
When did you first become interested in software dynamics? Was there a particular project or problem you can recall that set you off in this direction?
That's a good question. When I was at Digital Equipment, I got interested in careful tracing of what was going on in a single program. And that turned into being able to trace what was going on in an operating system, in this case, the VMS operating system. And one of the questions that the VMS designers had was sometimes the operating system would not respond to an interrupt very quickly at all. It would appear to be out to lunch for a while. So by doing microcode-based tracing of all of the instructions being executed, I got to find that when that happened, the swapper program had just started up and was holding on to the CPU and not taking any interrupts. And that was a real simple thing to fix once they knew what the dynamics were, but they had never been able to observe it before. So that was around 1980, 1981.
So do you feel that early software engineers, say in the 1970s, knew more about hardware than engineers typically know today?
Oh, certainly. In the 70s, lots of people wrote in assembly language. Optimizing compilers weren't very good. And so anyone who paid much attention to performance had to know a lot about what the real machine was. But it was also a much simpler environment. We were simply looking at really running just one program at a time.
So who is the target audience for the book?
There's sort of two target audiences. One is graduate students interested in software performance, and the other software professionals who are actively writing complex software, for instance, at places like Google or Facebook or Amazon that have lots of interactions with people or with machinery.
So I'm curious, performance is obviously a major concern with understanding these dynamics, but are there any other goals that might lead us to want to understand this runtime behavior in detail? Is it strictly performance?
To my mind, it is. I mean, that's what the book is about. The industry has lots of tools, observation tools and software and hardware help to understand the average performance of simple programs, and almost no tools to understand what delays are when you care about response time and you have 30 or 40 different programs running. So I've tried to look at the harder problem of understanding the dynamics in a very complex environment, which is also the environment you would find in simple embedded controllers. The embedded controller for Tesla Autopilot has about 75 different programs running at once, and it has responses that it needs to make essentially every video frame.
So I remember the difference between the average case and, I guess, maybe not the worst case, but you mentioned the tail latency typically is one measurement to find these slower cases. Can you explain a little bit more about what tail latency is?
Sure. If you have something like a piece of a program that's responding to requests for email messages from users all over the world, and a user is sitting there and says, I want to look at my next message, and it pops up. I want to look at my next message, it pops up. I want to look at my next message, and there's a 4-second delay, and then it pops up. I'm interested in that variance in the things that on occasion are slow, even though the average performance is very good. Some of those slow responses are just annoying, but some of them are life-threatening when you're dealing with big machinery.
Okay, I think that's a good introduction. The book is centered somewhat around what you call the 4 fundamental computing resources, I guess the hardware resources, which are the CPU, memory, disk, and network. And then you add locks and maybe queues as critical software resources. Before we dive into these, there's a utility you discuss in the book, which is available on your GitHub site called KUtrace. Can you tell me a little bit about what prompted you to write this utility? When did you have the idea for it, and just kind of how did it get developed?
Sure. The idea came about around 2006 when I was working at Google, and we had intermittent delays in web search and finding advertisements to deliver and all sorts of the software services. And no one knew why those delays occurred. So I decided to build an observation tool that would show us at least what was happening in Gmail or in search or whatever. And from my previous experience, I knew that doing something like tracing every function call inside the operating system or tracing every piece of code in hundreds of applications, so that would be much, much too slow, because the delays occurred usually during the busiest hour of the day in live data centers. They weren't things that we could find by running offline, by running canned test programs and stuff. So I came up with the idea of tracing all of the transitions between user mode and kernel mode, every operating system service call, every interrupt, every fault, every context switch, and worked with one of the Linux kernel people at Google to build an implementation that would trace just those transitions and trace it with very low overhead, less than 1% of slowdown of the CPU. Because my experience at Google was that if you went to the people whose job was to run the data centers and said, I have this great observation tool that has 10% overhead, so everything will be 10% slower, it's a really short conversation. They just say no. And if you say, there's about a 1% overhead, it's also a short conversation. They say, sure, we can't measure a 1% difference anyway. And if it's any number in between, it's a long conversation, and then the answer is no.
Yeah, that makes a lot of sense. And what really interested me about these chapters about KUtrace is you discussed in detail basically all of the design decisions behind what you did. It's almost like a walkthrough of your thought process and pretty extensive engineering that had to go into it. I'm going to get back to this if we have some time near the end, but I wanted to touch on all of the fundamental resources at least a little bit first.
Sure.
So the first resource you talk about is CPUs. You have a chapter where you give a great history lesson on CPU features. For example, you mentioned paged virtual memory first appeared in the 1962 machine, Manchester Atlas. Reading all of these descriptions of the features that seem to be additively growing on each other, I'm wondering, do CPUs always get more complicated over time, or has the trend ever been reversed? For example, people claim that ARM chips today are simpler than x86. Do you feel that's true, that some things do get simpler?
I think it happens in waves, that things get more and more complicated, and new instructions are added and features are added, and then performance gets too slow, or the power dissipation gets too large, or the clock cycle keeps getting longer and longer. And then there's sort of a step function, and somebody says, oh, well, we can do things much simpler. John Cocke did that by inventing RISC machines after complex instruction set machines just got slower and slower. We see, I'm not sure I would say today's ARMs are less complicated than x86, just because that architecture, including the 64-bit version, has grown and grown and grown. But we do as an industry go through periodic simplifications. DEC went through that with the VAX architecture, which turned out to be big and slow after a while. And the microVAX architecture was a subset that could be implemented more simply and more cheaply. And that extended the life of the VAX architecture by several years.
Yeah, I guess people talk about the pendulum swinging back and forth with architecture, both hardware and software. In the book, you explain how the hardware and the compiler can subvert your attempts to measure how long individual instructions take. So if I wrote a for loop to do an operation 10,000 times and timed that loop, what are some less obvious ways that the compiler or the hardware might make my timings inaccurate?
I'm going to give a little context first. The first section of the book for a graduate class, part of the purpose is to get a bunch of grad students who come from different backgrounds all on the same page. Some of them will know a whole lot about CPUs, some will know about memory or disk. And after the first 4 weeks, everyone knows a fair amount about all of those. So the timing an instruction, I give them the exercise of how fast is a single add instruction. You can read some time base, which we'll talk about, I'm sure, and do a whole bunch of adds and read the time base and subtract and divide and say, oh, here's how long it took. So I lead the students into lots of mistakes by giving them a program that does this. It's a little short 20 line kind of program, but it has a few flaws. If you compile it unoptimized and run it, you get some number like 6 or 10 cycles per add instruction. And if you compile it optimized and run it, you get some number like 0 cycles per add instruction. And the reason is that in the optimized form, the GCC compiler or most any other optimizing compiler takes out the entire loop because the result of all the adds is not used anywhere. And that's sort of leading the reader into the idea that you need to be careful that what you think you're measuring is what you're actually measuring.
Yeah, I've run into that myself trying to time instructions. And I think I went down that road of feeling like I needed to print out some final sum or something to tell the compiler that I actually needed that result. And there's a number of other pitfalls and tricks you cover. When I started my career, CPUs always ran at a fixed frequency. Today, it seems like the clock frequency can vary dramatically over time. What challenges does this pose for timing or tracing operations? And do real CPUs in data centers, do the frequency, is it variable or do they tend to lock it down to something?
Varying the clock frequency is a technique for reducing power consumption and therefore heat generation. I think it first started with Intel SpeedStep in the 80s. And one of the things that gets heavily used when you're doing careful performance measurements is some time base that counts fairly quickly, a cycle counter. The 1976 Cray 1 computer had a cycle counter that simply incremented once every cycle. And it was a 64-bit register. You could read it, and you could literally read the cycle counter, read it a second time, and subtract, and you would get a difference of one cycle. So when we did the alpha architecture at DEC in 1992, I included a cycle counter in the architecture so that any program could read it. And a year or two later, cycle counters started showing up all across the industry. And they would count each time that the CPU did a clock cycle to execute instructions. And then a few years later, when SpeedStep came along, the effect was that when the CPU clock was slowed down to save power, the time for one cycle slowed down. And if you're using the cycle counter to measure wall clock time, suddenly it got way out of whack compared to wall clock time. And that matters, for instance, in the early Google file system, GFS. The cycle counter was used along with a multiply and an add to reconstruct the time of day, and that was used to timestamp files. And if you ran on a machine where time appeared to go backwards, the file system would crash. And the effect when SpeedStep came in was that they could not use it. They had to keep running the clock at a constant rate, otherwise the software would get confused and crash. Subsequent to that, people created the so-called constant rate cycle counter, which actually just counts time. And it counts at the same rate independent of the power saving. Typically, it would count at 100 megahertz, increment once every 10 nanoseconds. And that gives a much more stable time base.
Yeah, in my work, I've run into the situation, I think it was the RDTSC instruction on x86, and you had to also worry about whether your program had moved from one CPU to another and whether the clocks were synchronized across CPUs. And I just remember there was a lot of pitfalls there. So that's a little bit about CPUs. There's a lot more detail in the book, especially about the history and the complexity. So let's move and talk about memory. So the chapter on memory had a lot of information about caching and the complexities of caching, the difference between an algorithm that fights with the cache versus one that's very cache aware can be extremely large. Do you feel this is something a lot of software could do better? Is cache awareness something that is often ignored?
A lot of software is not very sensitive to the cache behavior, but some important software is. So if you're looking at inner loops of matrix multiply or something, it makes a huge difference. If you're looking at the Linux operating system running, the operating system code isn't terribly sensitive to cache behavior, except when it's doing something like bulk moves of a bunch of data from one place to another place. So it's sort of a mixed bag. On the other hand, if you don't know anything about caches, and essentially caches are a speed-up mechanism, and they're wonderful when they work as intended and when the software uses them as intended. But if you end up, perhaps by mistake, with software that defeats the caching mechanisms, what happens is your performance just falls off a cliff. And that happens all over this industry, not just with caches, it happens with networks. If you have magic hardware that offloads TCP packet assembly or something, maybe that hardware handles 8 different active streams, but if you have 9, suddenly the performance drops by a factor of 100. So all of these speed-up mechanisms, as chips get more complicated and issue instructions out of order and 5 instructions at a time, they're wonderful until you step off the edge of the cliff. And to know about that, you have to actually understand a little bit about what the hardware is doing so that you recognize what you've done to yourself when you step off the cliff.
So one thing that interested me was all the different types of caches, different cache levels, sizes, associativity. Is it possible to have an algorithm that's sort of roughly cache aware, but it's not tuned to a specific CPU? Is there sort of a spectrum of cache awareness?
Yeah, the main thing is to, when you're accessing multiple uses of data, to have them stored near each other. And if you have some huge amount of data, hundreds of megabytes, if you go to access part of it, try to access other parts nearby rather than being just totally scattered. That's the main thing.
A term I've come across is structure of arrays versus array of structures. And I guess structure of arrays means what you're saying, that the same type of data is sort of packed in without anything in between. Have you heard that terminology before?
Not recently. I heard it a lot in the 70s. If you have something like 6 parallel arrays and you're going for one item in each of the 6. If they are literally separate arrays, then you're looking at 6 different cache accesses. If you have an array of elements that are more than one, that are all 6 pieces physically together in memory, then you may be looking at one cache access or one cache miss. I have a quote I want to throw in here. That's from Don Knuth. That's in the book in chapter 2. The quote is, "People who are more than casually interested in computers should have at least some idea of what the underlying hardware is like. Otherwise, the programs they write will be pretty weird."
Yeah, definitely. I think that awareness of hardware is a huge theme in the book. Continuing on memory for a little bit there was a section about the pre-charge cycle of DRAM, row versus column axis of memory. I've definitely witnessed the impact of caching on my software, but I've never thought about DRAM access at this level of detail. Have you seen issues where these hardware details affect performance, or is it less significant than, say, caching?
I've seen instances where it does affect performance. DRAMs, dynamic random access memories, aren't random. The internal implementation in the transistors, if you read someplace that's near where you last read in a particular bank of RAM, it'll be faster than if you are always scattered about reading just a few items here and there. So the effect is much like caching. The DRAM chips internally cache like 1,000 bytes in one access. And if you reuse bytes within that, it's faster than if you go to a completely different group of 1,000 bytes.
Yeah, I guess the term locality of access, that jumps to mind related to this. So that's a little bit about CPUs and memory. Let's move on to talking about disk. So you have disks as the third fundamental computing resource. You include a lot of details about both hard disks and solid-state disks, SSDs. Let's talk mostly about SSDs here, since increasingly what people are using, at least in their own machines. So like with memory, you discuss several ways that hardware and low-level software can subvert your attempt to make simple measurements. Can you mention some of the ways here that would subvert your ability to measure how long a disk access would take, or a disk read or a disk write?
Or an SSD access?
Yeah, I think for an SSD.
Yeah. When you go access, let's say you want to read a 4K block off of an SSD, there's all these mechanisms under the covers that are, quote, helping, unquote, you. The operating system file system almost surely has a cache of recently accessed storage data. And so you may do a read and you simply hit in the file cache and never go to the device. Most SSDs actually have a small RAM inside, static RAM inside the SSD package, and they will read from the flash memory into the RAM and then supply data from the RAM. This is most useful when you're writing, to buffer up a whole bunch of writes and then write them all to the flash transistors all at once. But you may find that you do reads that hit in the RAM that's inside the solid state drive and don't suffer 10 or 50 or 100 microseconds to get to the real flash transistors. So everyone has their finger in the pie trying to speed things up and occasionally slow things down.
So reading about the specific electrical properties of SSDs and, again, the charge cycles, I guess I got a little confused on what is the difference between DRAM and SSD. Is the underlying technology totally different? Of course, SSDs keep their data when the power's off. But other than that, are there similarities between the two?
They're really completely different. The flash transistors can hold the value that you set in them, a 1 or a 0, for 10 years or more. But they wear out. If you write them 100,000 times, they stop being able to separate ones from zeros. The amount of charge that's stored inside the floating transistor degrades over time. I'm not sure if that fully answered your question.
Yeah, well, that's definitely a huge difference. I think that what I really liked about the book is that it packed in a lot of the details, the hardware details that I had come across at various points in my career, but it packed them into one section. So even in the hard disk drive section, I thought was really interesting to read about all of those details put together.
I should say one other thing about the SSDs. When you write an SSD, the actual write of the flash transistors assumes that they've already been set to all ones, and then you selectively change some of them to zeros. And the erase cycle that sets them to all ones takes a long time. It takes like 10 milliseconds. And most flash chips, when you are doing an erase cycle, they can't do anything else. And the effect that an application programmer can see is if you're doing writes to an SSD, reads that are intermixed may be now and then completely delayed by an extra 10 milliseconds because the chip can't do any reads while it's doing an erase cycle. And that really is noticeable in data center performance and in some other real-time contexts.
Yeah, that's definitely a super low-level detail. And I guess when I first started to read the chapter, I assumed that SSDs were going to be more or less, perfect performance compared to hard disk drives. So it was pretty interesting to hear about they have their own peculiarities that can surface. So that was CPUs, memory, disk. Let's move on to network. The networking chapters talk a lot about remote procedure calls. When I think of accessing a resource over the network, I'm usually thinking about HTTP REST. Are remote procedure calls something different, or is REST a type of remote procedure call?
Remote procedure calls are used to connect together lots of machines that are sharing work. They don't show up much if you just have one computer or you have a small number of computers that don't interact. A remote procedure call is like a procedure call within a single program, where procedure A calls procedure B, except that B is running on a different machine somewhere, typically in the same room, but sometimes across the country. And the arguments to that call are shipped across the network to the other machine where it runs procedure B and gets some answer, and then the answer is shipped back over the network to the caller procedure A, which then continues. And that can be incredibly useful for having something like a web search at Google, where the computer that gets a search from a user immediately fans it out to 100 other machines using a remote procedure call for each of those machines to do a piece of the work. And those fan it out actually to another 20 machines each or something. So there's 2,000 machines. And then the answers come back and are merged together across those 2,000 machines, the 100 machines, the one machine. And then an HTML page is put together and sent to the user, all in a quarter of a second or so.
So specifically, a remote procedure call could be implemented by different networking technology. You're just using it as kind of a generic term for any type of call to a remote machine, or are you specifically talking about a certain type of?
No, just any generic call. And most of the networking chapter is about waiting on what the other machines are doing or being able to understand who's waiting when. And the same could apply to remote access to files. You have distributed file system across many machines.
Okay. I said we're not going to talk too much about KUtrace yet, but in the chapters about networking, you have a long section, I think, talking about RPC IDs and how you need to record those IDs in order to do a trace. Can you talk a little bit more about that? Because I wasn't totally clear on how you're able to deduce so much information from just really short IDs.
Okay. If you look at something, I'll pick a disaster that I didn't work on at all. The U.S. government's rollout of signing up for Obamacare. That was a set of computers that performed very poorly and were usually not working, put together by about 30 different companies, none of whom had any responsibility for the entire works actually delivering signups to citizens. But they were all connected together so that whatever a citizen did would send messages between lots of different computers. And when you're trying to figure out why some response either doesn't happen at all or happens very slowly, you need some way of figuring out which message relates to which, in this case, citizen's request or carriage return or whatever. And so giving all of the messages some kind of identifying number, which keeps changing, every message has a different number, is an underpinning that's absolutely necessary if you want to do any kind of performance analysis of where did all the time go. So it can be just a simple number, 32 or 64-bit number.
I see, yeah. So you're recording these on the different machines, and that allows you to trace what work was done on behalf of that call?
Yeah, and the messages between the machines, each message includes transmitted over the network, that particular ID number.
I see. Okay, yeah, that makes sense. How about this term slop you used in network communications? It sounds like a very informal term, but how do you measure it and how do you decrease it?
Yeah, well, if you have two machines connected with something like an Ethernet, and machine A sends a message or request to machine B, and machine B gets that and works on it and sends an answer back to machine A, and machine A gets the answer. And that whole round trip takes a long time, so you're concerned about understanding what's going on. You might look at the time on machine A when it sent the request and the time also on machine A when the response came back. And then go over to machine B and look at when the request came in and when machine B sent the response. And maybe on machine A, the whole works took 200 microseconds. And on machine B, between the time it got the request and it sent its answer, there was only 150 milliseconds. Let me do all this in milliseconds. So the sender sees 200 milliseconds. The server, in this case, sees 150 milliseconds. And the question is, where did the other 50 milliseconds go? That's the slop. It's the difference between the elapsed time the caller sees and the elapsed time the callee sees. And if the slop is a few microseconds, that's perfectly normal. And if it's tens or hundreds of milliseconds, somebody dropped the ball somewhere. Maybe within the kernel on the sending machine of the request, maybe in the network hardware, maybe in the kernel on the receiving machine, or maybe the receiving machine's application program didn't bother to get around to asking for the next piece of work. And whenever there's a delay like that and you talk to a bunch of software programmers, it's real easy to point to it's somebody else's problem. And it's real hard to figure out where the actual time went.
So this might be related. Earlier this year, I saw Facebook released an open source hardware implementation of a time card that contained a miniature atomic clock chip. They presumably use this to keep time synchronized between servers in their data center. You go into some detail about how we can synchronize traces from different machines if the clock is different. Do you feel that tightly synchronized clocks are necessary? Are they worth the effort of having customized software? Or can we just deal with the clocks differing by a certain amount?
I'm not a fan of expensive high-resolution clock hardware. Google data centers, for instance, have a GPS receiver on the roof or something, and then the GPS time is forwarded via software and networks within a data center room that might be an acre or something, forwarded to all the machines. And some other data center in some other state has its own GPS receiver, etc. But if you have only one, it's a single point of failure. I mean, suddenly the whole building doesn't know what time it is. So in fact, you need like 3 of them, and then you need to figure out which one to actually believe if they're different. And there's also places like Facebook or papers from Stanford about very, very careful hardware that can keep clocks on different CPU boxes synchronized within a few nanoseconds of each other. And for understanding the dynamics of application software, I found all that to be unnecessary. That it's good enough to simply use whatever 100 megahertz kind of cycle counter clock there is on one machine and whatever one there is on another machine. And they'll differ, maybe by the time of day might differ by 10 milliseconds or so. And it might drift so that after an hour it differs by 11 milliseconds. But if you have time-stamped interactions between those machines, and you have some that don't have big delays are uncommon in individual round-trip interactions, then you can, in software from a whole bunch of timestamps, you can align the clocks between the two machines in order to make sense of some trace of what was happening. And you can pretty easily achieve 5 or 10 microsecond alignment. So one of the things I encourage the readers to do and walk them through is you don't really need expensive, fancy clock hardware. You can do perfectly well with different machines that have slightly different clock speeds and align them in software.
Yeah, and you did walk through that in pretty extensive detail, and it seemed like not incredibly fancy, but it was definitely using statistics and, algorithms that were maybe more than someone would come up with just off the top of their head. So those were 4 major hardware resources: CPU, memory, disk, and network. You include locks as, I guess, the 5th major resource. Why are software locks almost as important as hardware? And do you feel this is new, or this has been changing over time, or would you have always included locks as a primary resource?
Software locks are used to keep multiple threads of execution from going through the same critical section simultaneously. If 2 things go through something like reserving the code that reserves an airplane seat simultaneously, they might both get the same seat. So software locks weren't around in the 1950s, but have become really important these days when you have large machines doing lots of different work. You have operating systems that run the same operating system image on 4 different cores on a single processor chip. There are pieces of the operating system where you need to be sure that 2 different cores aren't updating some internal data structure simultaneously. So there's software locks all over. I once did a search through the Google code base when I was there. The whole code base is searchable, of course, since it's a search company. And there were like 135,000 different locks declared, software locks. Most of the delay in real-time responses in that environment is delay waiting on locks. It's not waiting on all the other things that the book talks about. So yeah, they're important.
You also talk about queues. I assume that queues are often implemented with a lock. So is this just a special case of locks, or is there anything about queues which deserves to be focused on as its own different resource?
I didn't make the context for the chapter on queues quite clear enough. I was specifically interested in work that is done in pieces. A little piece is done, and then the package of work to be done is placed on a software queue, and then later some worker program picks up that piece of work off the queue, does the next step or next piece of the work, puts it on a queue for some other thread, and eventually, after 4 or 5 steps, the work is completed, and then the results are sent out, or the response is done, or whatever. So queues themselves have some locking at the very bottom of the design to make sure that 2 different things aren't being put on a single queue simultaneously. But the chapter on queuing is more about the next level up of if you have pieces of work getting queued up, if they get stuck in the queues too long, that's a source of delay.
You briefly mentioned lock-free programming, where special CPU instructions like compare and swap are used. I felt like a lot was made about these algorithms a number of years ago, but lately I've not been reading as much. Do lock-free algorithms solve all the problems of locks, or what problems still remain?
They don't remove the need to do locks, but they can give you some low-level pieces that don't have to block and wait as you would if some other thread is using a software lock that you need. They're just instructions that atomically within a single instruction move 2 pieces of data around instead of just 1 piece. And they guarantee that 2 different CPU cores aren't moving the same 2 pieces simultaneously such that they get shuffled out of order.
So you feel that lock-free algorithms?
Yeah. Lock-free algorithms are important at a very low level, and the underlying hardware instructions are in all machines now.
Okay, that makes sense. So we've talked about these 5 fundamental computing resources, maybe 6 if you count queues separately. And we've talked a little bit about KUtrace. 2 other big sections in the book are about observing and reasoning. One of your refrains in the book is asking people to predict what they expect to find before measuring it. Why is this prediction step helpful, and when did you start doing this yourself or fall into the habit of trying to make predictions about performance measurements?
See, I'll answer the second part first. I started making predictions when I took Don Knuth's fundamental algorithms class, and we counted cycles in this fake mix processor. And if you don't know how many cycles or how fast or how much time something should be taking, then you run some program on some computer and you get some performance numbers and you say, okay, that's what it does. And you have no basis to question whether that makes any sense. So for instance, the half-assed is an ad where I lead the students into optimized code that simply deletes the loop and says an ad takes 0 cycles. If you haven't written down ahead of time that you think an ad might take 1 cycle, I have students who say, oh, an ad takes 0 cycles, and turn that in as the answer on their homework. So the point is to first raise a reader's awareness that you can actually estimate within a factor of 10 how long things should take for almost anything. And then you have a little touchstone that if you then go run some program and measure it a little bit, if the measurement you get is wildly different than your estimate, then there's some learning to be done. You might learn that your thought process for the estimate was way off. You might learn that the program is way off. You might learn that it's a little bit of each. So I think it's a really important professional step for software programmers who care about performance.
Yeah, I can definitely see that. So how would you say it's related to the scientific method, like making a hypothesis, doing some tests, looking at the data? It sounds like as engineers, we shift into doing a little bit of science and then shift back into engineering. Do you see a connection between the two?
Yeah, I think that's true. The estimate is a bit like a hypothesis. If you're looking at some piece of biology and you think that some protein has some action, you make that as a hypothesis, and then you try to design experiments to see. And in this case, you make an estimate of speed or performance, and then you see what happens, and then compare. And if you tried to do science by having no hypothesis, you just say, let's do a bunch of experiments and see what happens, but we have no idea what that means, you don't make progress very quickly.
Yeah, I can definitely tell in my own work sometimes when I'm running against the limit of what I understand, I'll sort of get this anticipatory feeling like, well, at least I'm going to learn something here with my next task because it just has to reveal something. Another mental model from the book that almost sounds too simple to consider a model, but actually I think is helpful, is you say when your software is running too slowly, it's either not running or it's running but running slowly. Why is it worth keeping those two as separate possibilities? And I guess it could be a combination of the two also.
Oh, they're separate because the way you fix it is completely different. If you have a program that's occasionally slow doing some operation, it could be because that program is on the slow instances executing a whole lot more code. It goes off does some subroutine call you weren't expecting to happen, and that only happens now and then, and it goes off and does a whole lot more work. That's one choice. The second choice is it's executing exactly the same code as fast instances, but there's something interfering with that code somewhere around the shared hardware, some other program or the operating system that's making it run more slowly than normal. And then the third choice is that it's not running at all. And as an industry, we have lots of tools and profilers and things that pay attention to where the CPU time is going, but we're very weak on tools that say, oh, you're not executing at all, and here's why. So in the case of you're executing more code than normal, you need to find what the extra code path is. In the case of executing the same code but slowly, you need to find what other program or piece of the operating system is interfering and how is it interfering? Is it thrashing the cache? Is it taking over major portions of the CPU that you're trying to use? Is it loading down the network? Whatever. It's only one of 5 things. And if you're not running at all, then you need to go understand why the program isn't executing, what it is that it's waiting for, and then go fix how come the thing it's waiting for took too long. So in some cases, you fix the program you're working on. In some cases, you fix other programs.
Yeah, I think I remember from the book one of the examples of executing code that you didn't expect, and it was actually preparing a debug value or preparing some information that was then not even used. And so the investigation was difficult to find this case, but the solution was actually very simple in terms of just not doing that extraneous work. So I can see how that's a very different case from it's executing the exact thing you expect, but slowly. So yeah, they're definitely different.
And that was a real example from Google that took us about a month to track down why some service would go out to lunch for a little while. And we eventually found, there's this big piece of debug code that's running, and then the results thrown away. This happens in large software. Nobody's a bad programmer. It just, you end up with things like that after a while.
Yeah, and so you definitely feel like you're discovering these traits. So one thing I enjoyed was you mentioned the difference between batch processing, or I guess pipeline processing or data processing, versus user-facing transactions, and how, for instance, your CPU utilization is, your ideal CPU utilization is different in those cases. Can you speak to, have you dealt with both of those types of cases, or is software dynamics more of a concern with one of those types?
The software dynamics are more of a concern in time-sensitive code. A lot of our industry focuses on simple programs that start and run and stop, and they model them with benchmarks that run on empty machines. And the whole point of the benchmark is if you ran it 5 times in a particular machine, in a particular configuration, you should get 5 answers, 5 time measurements that are about the same. And then the marketing people take over from there. But that's not a very good model at all of software that's on the other end of your cell phone or in your cell phone, where you're waiting for something to happen. So programs that run in the background are run in batch, and nobody's waiting on them particularly strongly. They can run for a couple hours, and it doesn't matter if it takes 2 hours or 2.5 hours. That's a very different environment than I hit carriage return and I want something to happen on my screen. In that environment, with the time sensitivity, you never want the CPUs to be 100 or even 90 or even 80% busy. While in the benchmarking environment or the high-performance physics environment where you're doing lots and lots of matrix calculations, the goal is to make the CPUs 100% busy. So they're very different environments.
Yeah, and that's a distinction I've run into also. You're either trying to sort of soak up all of the hardware resources available, or you're trying to reserve some for when you have a spike in usage or when you need it. So you have 2 neat examples in the book. One was, I think you were just investigating, or you found this documented. It was a IBM 7010 from 1964. And this was one of the earliest cases you found of someone using the type of tracing techniques that you talk about to investigate a real performance problem. I assume it was performance. And then maybe in the next chapter or later in that chapter, you talk about some of your work investigating a specific problem with performance in Gmail in 2006. So these examples are more than 40 years apart. What can you say about the process of investigation that was the same and what was different? We don't have time to talk about the details of the investigation, but I'm just interested, were you left with thinking that the process itself has remained much the same, or has there been, wildly different processes?
I think the processes are surprisingly similar. I should say a word about tracing versus other observations. If you are dealing with problems that are reproducibly slow, you can go find those and fix them sort of working offline. You don't have to deal with a user-facing real-time environment, time-sensitive environment. But if you have occasional hiccups in time-sensitive software, you don't know when they're going to occur. And if you don't know when they're going to occur, you need to watch for quite an interval of time. You need to watch everything that's going on, and then hope that you get some of these hiccups so you can track down what the root cause is and fix it. And so there's a lot of observation tools that do logging and profiling and stuff that sort of merge together a lot of data and give you some aggregate numbers. And to really see these anomalous execution paths, you need to trace everything that's happening over on the order of a few minutes. That's hard to do. It's particularly hard to do with tiny enough overhead that you're not just distorting what you're trying to learn about. And that difficulty of tracing what's going on has been the thing that's constant from the 50s to now. The IBM 7010 people, they built a whole box of hardware to watch the program counter value on some instruction bus every cycle for seconds. And it was a one-off pile of hardware at someplace like Rochester, New York. And that was the only way they could see what the programs were really doing. And the same thing now, it's real hard to build low enough overhead tracing software. You get lots of high overhead tracing software instead. And then you can't use it in a real-time environment.
Yeah, I had forgotten they built custom hardware to observe the machine. Well, I think we're going to start wrapping up. Is there any resources you'd like to point out where people can learn more about the book or about yourself? And I'll put any links you mention in the show notes so people can look them up there.
Okay. The two main places where the book is available are on the Pearson or Addison Wesley website, which is called informit.com. That website, in addition to showing the book, has all of the code that goes with the book and has started to have reviews. The other place is Amazon, which I think is just now getting their first shipments of boxes of books.
Okay, that's great. Yeah, and this is being recorded in December 2021, so that's what we're talking about. How about yourself? Any other links to recommend or resources?
No, I'm not really on social media very much. I'm on LinkedIn.
Okay, I'll definitely add that to the show notes. Well, thanks so much for being on the episode. I really enjoyed reading the book. You have a lot of great technical detail that we didn't get into here in the episode. And I would say that some of the chapters read somewhat like a mystery or a thriller. So it was really interesting to go through those examples. Do you have anything else you want to mention?
Yeah, some of the readers may enjoy the 40-plus index entries under screw-ups. There's lots of examples of real-world screw-ups in the book.
Yeah, I remember those. Okay, well, thanks a lot. This is Philip Winston for Software Engineering Radio. Thanks.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.